May 24, 1867. Brooklyn Heights, New York. The engineering assessment from European bridge experts would never fully capture the impossibility of what one American engineer was proposing that spring morning. 1,595 feet of East River water separating the nation's largest city from its third largest. No suspension bridge in history had ever spanned more than 600 feet. European masonry arch bridges, the proven method for major crossings, maxed out at 500 feet. Recent French suspension bridge failures had killed hundreds, proving the concept unworkable at this scale. Yet John Roebling was sketching cables made from thousands of individual steel wires, twisted together using techniques that defied everything European engineering wisdom said was structurally sound. Hemp rope, 7 inches thick, proven reliable, was how bridges carried loads. Wire rope was experimental, untested. The forces across 1,500 feet would snap any cable ever manufactured. 8,000 miles from European workshops, the most decisive engineering revolution in bridge-building history was about to begin. Not through superior stone masonry, not through proven European methods, but through one immigrant engineer's impossible cable design that would make European experts question everything they thought they knew about what American innovation could achieve. The hemp rope snapped with the sound of a gunshot echoing across the Allegheny Mountains. John Augustus Roebling watched in horror as the 7-inch thick cable, costing $300 and supposedly engineered for exactly this type of load, parted under strain. The canal boat, loaded with 2 tons of Pennsylvania anthracite coal, careened down the steep incline of the Allegheny Portage Railroad like a runaway freight train. 2 workers who had been guiding the boat never had a chance to jump clear. The hemp rope, which had seemed so substantial that morning when Roebling inspected it personally, now lay in twisted, frayed sections along the mountainside. This was the 3rd rope failure Roebling had witnessed in 18 months working as a surveyor on Pennsylvania's ambitious canal system. Each time the same sequence: hemp rope stretched to its breaking point, workers scrambling for safety, cargo scattered across the mountain terrain. Each time the same explanation from supervisors: hemp rope is proven technology. That's how we've always moved freight over these mountains. Sometimes these things happen. But Roebling's Prussian engineering training had taught him to question everything that killed people repeatedly. Walking among the wreckage that October afternoon in 1837, he calculated the forces that had just destroyed 2 lives. Hemp rope possessed roughly 5 tons of tensile strength when new. After one season of mountain weather, rain, snow, temperature changes, that strength deteriorated to perhaps 3 tons. The canal boat system required moving loads of 4 to 6 tons regularly. The mathematics were deadly simple. They were operating beyond the material's capacity every single day. That evening, in his cramped boarding house room in Johnstown, Roebling pulled out a technical journal he had been carrying since leaving Prussia 2 years earlier. The article, published by a German mining engineer, described experiments with iron wire rope in the coal mines of the Harz Mountains. Instead of organic hemp fibers twisted together, the Germans were experimenting with metal wires, dozens of individual iron strands wound around a central core. The engineering principle fascinated Roebling. Metal maintained consistent strength regardless of weather conditions, and iron wire could be manufactured to precise specifications that hemp could never match. The next morning, Roebling requested permission to examine the failed hemp rope sections more closely. What he discovered confirmed his suspicions about organic materials under industrial stress. Hemp fibers, when magnified, showed inconsistent thickness and internal rot where moisture had penetrated the rope's core. Individual fibers had different breaking points, meaning the rope's overall strength depended entirely on its weakest components. Iron wire, by contrast, could be manufactured with uniform tensile strength and would not deteriorate from moisture exposure. Roebling spent the following weeks obsessing over wire rope mathematics. If each individual iron wire could support 300 pounds, then a rope containing 20 wires could theoretically support 6,000 pounds, more than any hemp rope ever manufactured. The challenge was not the theoretical strength, but the practical construction, how to twist dozens of iron wires together without creating stress concentrations that would cause individual wires to snap under load. The breakthrough came during a December blizzard that shut down canal operations for 3 days. Trapped in his boarding house with nothing but technical journals and calculation paper, Roebling worked through the mechanical engineering of what he would later patent as spiral laying of wires around a common axis without twisting individual wires. Traditional rope construction involved twisting fibers together, which created internal stress and reduced overall strength. Roebling's innovation involved laying wires parallel to each other around a central core, then wrapping the entire assembly with additional wire to hold everything in position. This eliminated internal twisting stress while maintaining flexibility. By spring of 1838, Roebling had convinced his supervisors to let him construct experimental wire rope using his patented method. Working in a rented barn outside Pittsburgh, he hand-twisted iron wire purchased from local blacksmiths into his first prototype, a 1-inch diameter wire rope containing 48 individual iron strands. When tested against a 7-inch hemp rope costing $300, Roebling's wire rope demonstrated 6 tons of tensile strength at a fraction of the cost and weight. The Pennsylvania Portage Railroad conducted official tests in May 1838. Roebling's wire rope lifted loads that broke every hemp rope in their inventory. More importantly, the wire rope maintained consistent strength through an entire season of mountain weather, rain, snow, and temperature extremes that would have destroyed hemp rope in weeks. But institutional resistance proved more stubborn than engineering problems. Canal supervisors, many of whom had invested in hemp rope suppliers, questioned whether wire rope could handle the dynamic loads of actual canal boat operations. Hemp rope stretched under load, providing cushioning that absorbed sudden impacts. Wire rope, being less elastic, might transfer shock loads directly to the boats and incline machinery. What if wire rope's superior strength actually created new problems by concentrating forces in unexpected ways? Roebling addressed these concerns through systematic testing throughout 1839 and 1840. He documented wire rope performance under every conceivable load condition: steady pulls, shock loads, repeated cycling, temperature extremes, and deliberate overloading. His test results, compiled in a detailed engineering report submitted to the Pennsylvania State Works Commission, demonstrated that properly designed wire rope outperformed hemp rope in every measurable category while lasting multiple seasons instead of requiring annual replacement. The vindication came in 1841 when the Pennsylvania Portage Railroad officially adopted Roebling's wire rope for all 10 inclined planes of their mountain crossing system. By 1849, every major canal and railroad in Pennsylvania had converted from hemp to wire rope, eliminating the rope failures that had killed dozens of workers over the previous decade. But Roebling was already thinking beyond Pennsylvania's mountains. In his private notebooks, he sketched suspension bridge designs using wire rope cables that could span distances no European engineer had ever attempted. The same twisted wire principles that solved Pennsylvania's canal problems might revolutionize bridge construction itself if someone had the audacity to scale wire rope technology to dimensions that would dwarf anything built in human history. Washington Roebling stared at the metallurgical reports spread across his father's desk in their Trenton wire rope factory. The numbers told a story that would either revolutionize bridge construction or destroy the Roebling family's reputation entirely. Steel wire, not iron, tested at 160,000 pounds per square inch tensile strength, nearly double the strength of the iron wire that had made their Pennsylvania canal system successful. But steel wire had never been manufactured at the scale required for John Roebling's Brooklyn Bridge design. 3,400 tons of steel wire, the largest single steel purchase in world history. The technical challenge went far beyond material procurement. European suspension bridges used prefabricated cables hoisted into position by massive cranes and derricks. The Brooklyn Bridge's 1,595-foot span eliminated that possibility entirely. No crane existed that could lift cables thick enough to support the required loads across such distances. Washington had spent months calculating cable specifications that seemed to defy physics. 4 main cables, each 15 3/4 inches in diameter, containing 5,282 individual steel wires. Each cable would weigh 870 tons and stretch 3,577 feet from anchorage to anchorage. The innovation that would make construction possible emerged from Washington's obsessive study of his father's wire rope patents. Instead of building cables on the ground and hoisting them into position, the Roeblings would spin cables in place using individual wires carried across the span by traveling wheels. This aerial spinning technique had never been attempted at such scale, but the mathematics were elegantly simple. Each steel wire would be carried individually across the river, laid parallel to previously placed wires, then compacted together to form the finished cable. The steel selection process consumed the entire winter of 1875. Washington traveled between Pittsburgh steel mills conducting tensile strength tests on samples from Bessemer converters versus crucible steel furnaces. Bessemer steel, produced in massive quantities, offered consistency and cost advantages. Crucible steel, manufactured in smaller batches, provided superior quality but at 3 times the price. Washington's testing revealed that Bessemer steel met strength requirements while crucible steel exceeded them significantly. The decision would determine whether the Brooklyn Bridge cables possessed merely adequate strength or massive over-engineering that could survive unforeseen stresses. Washington chose crucible steel and designed the cables 6 times stronger than calculated loads required. European engineering practice called for safety factors of 2 or 3 to 1. The Brooklyn Bridge cables would operate at 6 to 1, providing strength margins that seemed almost wasteful to contemporary engineers. Washington's justification, recorded in his private engineering notebooks, reflected hard-learned lessons from his father's canal rope failures. Unknown forces will test this structure in ways we cannot anticipate. The mathematics of safety require assumptions about loads, weather, and usage that may prove incorrect. Excessive strength costs money once. Insufficient strength costs lives repeatedly. The first public test of Roebling cable technology occurred on August 14, 1876. Washington had designed a temporary footbridge using a single steel wire stretched across the East River, not for public use, but to demonstrate that steel wire could support loads at unprecedented spans. The wire, manufactured to Brooklyn Bridge specifications, measured just 5/8 of an inch in diameter, but possessed strength equivalent to hemp rope 7 inches thick. E.F. Farrington, the project's master mechanic, volunteered to cross the East River in a boatswain's chair suspended from the single wire. 10,000 spectators gathered on both sides of the river to witness what many expected would be a spectacular failure. European engineering journals had published articles questioning whether any wire rope could maintain structural integrity across 1,500 feet without catastrophic stretching or snapping under dynamic loads. The East River crossing would provide definitive proof of American wire rope capabilities under conditions that no European engineer had ever attempted. Farrington's crossing took 18 minutes. The single steel wire, under the full weight of a man in his chair, stretched approximately 6 inches, well within Washington's calculated parameters. More importantly, the wire demonstrated no signs of stress concentration or failure at the tower connection points where European engineers predicted catastrophic failure would occur. When Farrington reached the Manhattan side and signaled success, the crowd's reaction could be heard across both cities. The Brooklyn Bridge had passed its first engineering test. Wire spinning operations began June 11, 1877, using machinery Washington had designed specifically for aerial cable construction. The traveling wheels, essentially pulleys that carried individual wires across the span, moved at precisely controlled speeds to maintain consistent tension and positioning. Each wire followed the exact same path, laid parallel to previously positioned wires, creating cables with uniform density and strength distribution. The process required mathematical precision. Each of the 5,282 wires in each cable had to be positioned within fractions of an inch to ensure proper load distribution. The scale of the operation dwarfed any previous wire rope project. Each cable contained 19 strands of 278 wires each. The strands were arranged in hexagonal patterns around a central strand. then wrapped with additional wire and painted with white lead to prevent corrosion. The completed cables would contain 14,060 miles of individual steel wire, enough to stretch halfway around the Earth. No previous engineering project had required such precise coordination of materials, manufacturing, and construction techniques. By October 1877, the first cable was nearing completion. Washington's aerial spinning technique had proven not only feasible, but superior to European hoisting methods. The wires lay parallel with perfect uniformity, and tensile tests on completed sections showed strength characteristics that exceeded even Washington's conservative calculations. The steel wire was performing exactly as laboratory tests had predicted, but scaled to dimensions that European engineers still insisted were impossible. The Brooklyn Bridge cables represented more than enlarged versions of Pennsylvania canal rope. They embodied a fundamental shift in engineering philosophy from European craftsmanship traditions to American industrial precision. Where European bridge builders relied on massive stone masonry and proven construction techniques, the Roeblings had created structures whose strength came from mathematical calculation and material science rather than traditional architectural methods. The wire samples that arrived at Washington Roebling's testing laboratory in January 1878 looked identical to the crucible steel specifications he had ordered from J. Lloyd Hayes Company. Same diameter, same surface finish, same manufacturer markings. But when Washington subjected the wire to standard tensile strength testing, the results revealed a deception that threatened to destroy the Brooklyn Bridge before construction could be completed. Hayes wire tested at 120,000 pounds per square inch, 40,000 pounds below the specified strength Washington had calculated as essential for bridge safety. The substitution was sophisticated. Hay had delivered Bessemer steel, manufactured to look like crucible steel, counting on the assumption that no engineer would test every shipment of wire arriving at the construction site. Washington's systematic testing protocol, inherited from his father's obsessive quality control methods, had caught fraud that could have killed thousands of people. The political dimensions of Hayes' appointment had always troubled Washington. Bridge trustee Abram Hewitt had blocked John A. Roebling's son's company from bidding on the wire contract, citing conflict of interest, concerns that seemed more designed to create opportunities for political cronies than protect public integrity. Hay possessed no engineering background, no metallurgical expertise, and no previous experience manufacturing wire rope materials. His primary qualifications appeared to be political connections within Brooklyn's democratic machine and willingness to submit the lowest bid for the wire contract. Washington's discovery of the wire substitution created an engineering crisis with no acceptable solutions. Cable spinning operations were already 60% complete. Removing the inferior wire would require dismantling thousands of feet of completed cable work, setting construction back by at least 18 months and adding hundreds of thousands of dollars to project costs. But leaving the inferior wire in place reduced the bridge's safety factor from 6-to-1 to approximately 4-to-1, still adequate for calculated loads, but eliminating the massive over-engineering margins Washington had designed to handle unknown stresses. The test results showed disturbing patterns beyond simple strength reduction. Some coils of Hayes wire met specifications exactly, while others fell significantly below requirements. The inconsistency suggested that Hay was mixing superior wire with inferior materials, creating cables with unpredictable strength characteristics. Washington's master mechanic reported finding wire samples that barely met minimum specifications alongside wire that exceeded requirements. The randomness of the defects made it impossible to predict which sections of the completed bridge might fail under load. Washington faced a decision that would define both the bridge's safety and his own engineering reputation. European critics were already predicting catastrophic failure of American suspension bridge technology. Any sign of compromised materials would provide ammunition for opponents who insisted that masonry arch construction remained the only reliable method for major river crossings. But replacing the inferior wire would require admitting that American quality control systems had failed to prevent contractor fraud on the nation's most visible engineering project. The engineering solution Washington developed demonstrated the mathematical precision his father had instilled in Roebling construction methods. Instead of removing the inferior wire, Washington would add 150 additional wires to each cable, increasing the total wire count and compensating for the reduced strength of Hayes materials. The additional wire would restore safety factors close to original specifications while avoiding construction delays that might doom the entire project. But the wire addition required modifications to cable spinning procedures that were already underway. Washington had to recalculate strand arrangements, anchorage loads, and tower stresses to accommodate the increased cable weight and diameter. The changes demanded precision engineering work performed under intense public scrutiny, with newspaper reporters documenting every delay and cost increase. European engineering journals published articles questioning whether American bridge builders possessed the technical competence to manage projects of this complexity. Washington's detailed analysis of the wire substitution revealed the scope of Hayes' deception. The contractor had purchased legitimate crucible steel for initial test samples submitted to Washington's laboratory, then switched to cheaper Bessemer steel for actual production while maintaining crucible steel pricing. The fraud generated profits of approximately $50,000, money extracted from public bridge funds while compromising structural safety. Hayes' political connections had prevented proper oversight of wire quality until Washington's systematic testing exposed the substitution. The corruption extended beyond simple material substitution. Washington discovered that Hay had subcontracted actual wire production to mills that specialized in inferior grades of steel wire, then applied surface treatments designed to disguise the material differences. The deception required coordination between multiple suppliers and deliberate efforts to defeat quality control testing. This was not accidental corner cutting, but systematic fraud designed to maximize profits while transferring structural risks to bridge users. Congressional hearings on the wire substitution exposed the political networks that had enabled Hayes' appointment. Abram Hewitt, despite his stated concerns about conflict of interest, had recommended Hay based on political relationships rather than technical qualifications. The hearing testimony revealed that multiple bridge trustees possessed financial interests in contractors bidding on bridge construction, creating exactly the conflicts of interest that Hewitt claimed to oppose when blocking Roebling's son's company. Washington's response to the crisis demonstrated engineering integrity that European critics had not expected from American contractors. Rather than concealing the wire substitution or minimizing its significance, Washington published detailed technical reports documenting both the extent of Hayes' fraud and the engineering modifications required to maintain bridge safety. The reports included complete tensile strength data, revised safety calculations, and explanations of how additional wire would compensate for material deficiencies. The additional wire installation began in March 1878 under Washington's direct supervision. Each new wire was individually tested before installation, and Washington personally verified the tensile strength of samples from every coil. The process added 4 months to cable completion schedules, but ensured that no additional inferior materials would compromise bridge safety. European engineering observers, expecting American construction standards to collapse under political pressure, instead witnessed systematic quality control that exceeded their own construction practices. By August 1878, the cable modifications were complete. The Brooklyn Bridge cables contained not only the strongest steel wire available, but also engineering margins that could withstand stresses far beyond any previous suspension bridge design. Washington had transformed a political corruption crisis into proof of American engineering integrity, demonstrating that systematic technical methods could overcome both material defects and political interference to produce structures that surpassed European engineering standards. The Fulton Ferry had crushed John Augustus Roebling's foot with the methodical precision of industrial machinery designed to move tons of cargo without regard for human obstacles. On July 15, 1869, while conducting final survey measurements for the Brooklyn Bridge Tower locations, Roebling had been standing on the ferry slip's wooden planking when the incoming boat struck the dock with unusual force. His right foot, caught between the ferry's hull and the pier structure, was mangled beyond any hope of surgical repair. The tetanus infection that followed demonstrated how quickly 19th century medicine could transform minor injuries into death sentences. Roebling, who had survived decades of dangerous engineering work in Pennsylvania mountains and canal construction sites, found himself bedridden in his Brooklyn Heights home while his body fought a bacterial invasion that 1869 medical science could neither treat nor cure. The wound itself, several crushed toes requiring amputation, should have been manageable for a man of Roebling's physical constitution. But the tetanus bacteria, introduced through contaminated dock debris, produced toxins that systematically shut down his nervous system. Washington Roebling received word of his father's condition on July 20th while supervising wire rope manufacturing operations in Trenton. The telegram's message was characteristically brief. Father injured, ferry accident, condition serious. Return immediately. Washington understood that his father's engineering philosophy demanded detailed contingency planning for every foreseeable disaster, except the random industrial accidents that killed experienced engineers with depressing regularity. John Roebling had calculated wind loads, traffic stresses, and material failures with mathematical precision, but ferry scheduling and dock maintenance fell outside his engineering control. John Roebling died on July 22, 1869, 24 days after the ferry accident. His final engineering notes, dictated to Washington during lucid intervals between tetanus spasms, contained detailed instructions for Brooklyn Bridge cable installation procedures and stress calculations for anchorage systems. Even as bacterial toxins paralyzed his muscular system, Roebling continued refining technical specifications for wire rope placement and tower construction methods. His death eliminated not only the bridge's chief engineer, but also the only person who fully understood the mathematical relationships between all structural components of his suspension bridge design. Washington inherited responsibility for completing the most ambitious engineering project in American history at age 32. With construction barely begun and European critics predicting inevitable failure of American suspension bridge technology, the transition from assistant engineer to chief engineer occurred without ceremony or fanfare, simply the recognition that Washington possessed more knowledge of his father's bridge design than any other living engineer. But theoretical knowledge and practical construction experience represented different challenges entirely. Washington had never managed a project involving hundreds of workers, millions of dollars of public funds, and political oversight from multiple government agencies. The underwater caisson work that began in 1870 represented engineering challenges that exceeded even John Roebling's original calculations. The bridge towers required foundations extending 78 feet below high water mark on the Brooklyn side and 71 feet below high water on the Manhattan side, deeper than any previous construction project had attempted. The caissons themselves were massive wooden and iron structures designed to create dry working environments on the river bottom, where crews could excavate tower foundations and place stone masonry. Washington personally supervised the caisson operations, working alongside crews in the compressed air environment required to keep river water from flooding the excavation chambers. The work demanded physical stamina and technical expertise that few engineers possessed. Compressed air pressure sufficient to hold back East River water created physiological stresses that were poorly understood by 1870s medical science. Workers experienced joint pain, breathing difficulties, and neurological symptoms that seemed connected to rapid changes in air pressure when entering and leaving the caissons. The first signs of Washington's illness appeared in May 1872, after extended periods working in the Brooklyn caisson at maximum pressure depths. The symptoms, severe joint pain, paralysis in his hands and legs, difficulty speaking, matched the caisson disease that had affected multiple workers, but with greater severity than previous cases. Washington's condition deteriorated rapidly, leaving him unable to visit construction sites or directly supervise foundation work during the most critical phase of tower construction. By September 1872, Washington was confined to his apartment in Brooklyn Heights, paralyzed from the chest down and dependent on his wife Emily for basic physical care. The decompression sickness had damaged his nervous system in ways that contemporary medicine could neither reverse nor adequately treat. European newspapers published reports suggesting that the Brooklyn Bridge project would be abandoned, citing the death of its original designer and the incapacitation of his successor as proof that American engineering had attempted construction beyond its technical capabilities. Emily Warren Roebling found herself thrust into a role that no woman had ever occupied in American engineering. Washington's detailed written instructions, dictated during periods when his speech remained clear, became the primary means of communicating construction decisions to site supervisors and workers. Emily learned to interpret technical drawings, understand steel specifications, and translate between Washington's engineering calculations and the practical requirements of construction crews. Her daily routine involved carrying messages between the bedridden chief engineer and the bridge construction site, serving as the human connection that kept the project operational. The bridge trustees initially resisted accepting construction directions delivered through Emily, questioning whether a woman could accurately convey complex engineering instructions or make technical decisions in Washington's absence. But Emily's consistent competence in translating between technical requirements and practical construction gradually earned respect from workers and supervisors who recognized that she understood the bridge's structural requirements better than most trained engineers. Her presence on the construction site became routine, and crews learned to trust her interpretation of Washington's written instructions. Construction progress slowed but never stopped during Washington's illness. The tower foundations reached completion in 1874, with Emily serving as the primary communication channel between Washington's engineering expertise and the construction crews executing his designs. The massive stone towers rose according to Washington's precise specifications, demonstrating that American engineering systems could maintain technical standards even when traditional project management structures collapsed due to illness and accident. European engineering journals, which had predicted immediate project failure following Washington's incapacitation, instead documented the continuing progress of Brooklyn Bridge construction under Emily's coordination. The bridge had survived the loss of its original designer and the illness of his successor through systematic engineering methods that did not depend entirely on individual genius. American engineering had proven more resilient than European critics expected, maintaining construction quality and technical precision despite unprecedented management challenges. Cable spinning operations reached completion on October 5, 1878, with Emily Roebling personally supervising the installation of the final wire strands. The completed cables represented engineering precision that surpassed every previous suspension bridge project. 14,060 miles of steel wire arranged in 4 cables, each containing 5,282 individual wires positioned with mathematical exactitude. Each cable weighed 870 tons and stretched 3,577 feet from anchorage to anchorage. The aerial spinning technique Washington had designed proved not only feasible but superior to European cable hoisting methods, creating uniformly strong cables that European engineers had insisted were impossible at this scale. The deck installation that began in January 1879 demonstrated the revolutionary structural innovations John Roebling had incorporated into his bridge design. Traditional suspension bridges hung roadway decks from vertical cables with minimal structural rigidity, making them vulnerable to wind-induced oscillations that had destroyed bridges across Europe. The Brooklyn Bridge employed Roebling's patented web truss system, a network of diagonal steel cables that connected the main cables to the deck structure, creating triangulated supports that eliminated dangerous bridge movement under wind loads or traffic stresses. Emily's role evolved from message carrier to construction coordinator as deck installation progressed through 1880 and 1881. Workers had learned to trust her technical judgment and accept her authority to make construction decisions when Washington's written instructions required interpretation or modification based on field conditions. Her daily presence on the bridge construction site, reviewing steel deliveries, and inspecting connection work, represented unprecedented female involvement in major engineering projects. European observers, initially skeptical of American construction management, found themselves documenting a bridge project that exceeded their technical expectations while operating under management structures they had never encountered. The steel suspender cables that connected the main cables to the deck structure required precision manufacturing and installation that tested American steel industry capabilities. Each suspender had to be cut to exact lengths calculated from Washington's mathematical models of cable deflection under load. The installation sequence demanded coordination between multiple work crews, positioning deck sections while maintaining proper load distribution across the main cables. Any errors in suspender length or deck alignment could create stress concentrations that might cause catastrophic structural failure. Washington's web truss innovation proved its effectiveness during winter storms of 1881 and 1882. European suspension bridges typically closed during high wind conditions because deck oscillations became dangerous for both traffic and structural integrity. The Brooklyn Bridge remained stable in wind conditions that would have made traditional suspension bridges unusable. The diagonal cable network transferred wind loads directly to the main cables and towers, eliminating the vertical oscillations that had destroyed bridges in France and England. The bridge's opening ceremony on May 24, 1883, attracted political leaders and engineering observers from across America and Europe. President Chester Arthur attended alongside New York Governor Grover Cleveland and Brooklyn Mayor Seth Low. The ceremony represented more than the completion of a single bridge. It demonstrated American engineering capability that European critics had insisted was impossible. The 1,595-foot span exceeded any suspension bridge ever built by 50%, using construction techniques and materials that challenged fundamental assumptions about structural engineering. Congressman Abram Hewitt's opening day speech acknowledged the bridge's technical achievements while attempting to minimize his earlier opposition to Roebling engineering methods. It stands before us today as the sum and epitome of human knowledge, Hewitt declared, conveniently omitting his role in blocking the Roebling Company from wire contracts and enabling the corruption that had nearly compromised bridge safety. The political rehabilitation of the bridge's critics demonstrated how engineering success could transform skeptics into advocates, but only after American innovation had proven European engineering assumptions wrong through actual construction results. The first train crossing on May 25th provided definitive proof of the bridge's structural capabilities. A fully loaded passenger train weighing over 200 tons crossed the 1,595-foot span without producing measurable deflection in the main cables or deck structure. European engineering calculations had predicted that dynamic loads from railroad traffic would cause dangerous oscillations or structural failure in any suspension bridge at this scale. The Brooklyn Bridge absorbed train loads while maintaining structural stability that European masonry arch bridges could not match. Public usage during the bridge's first months of operation exceeded all traffic projections. Daily pedestrian crossings averaged 15,000 people, with weekend totals reaching 25,000. The bridge handled traffic loads that would have overwhelmed any previous river crossing while demonstrating structural reliability that impressed even skeptical European observers. The steel wire rope that had begun as John Roebling's solution to Pennsylvania canal problems had evolved into structural technology capable of supporting modern urban transportation requirements. The economic impact extended far beyond bridge tolls and construction costs. John A. Roebling's Sons Company received contracts for wire rope systems on major bridges across America, including the proposed George Washington Bridge and Golden Gate Bridge projects. The technical reputation established by Brooklyn Bridge success created market demand for American wire rope technology that challenged European dominance in structural steel and suspension bridge construction. American engineering firms began winning international contracts based on demonstrated capabilities rather than theoretical proposals. Worker testimonials from the construction project reflected pride in American engineering achievement that transcended individual company loyalties. That German fellow knew what he was talking about, reported the master mechanic who had supervised cable installation. Wire rope changed everything about how bridges get built. We did something here that nobody thought was possible. The Brooklyn Bridge had transformed from an experimental project criticized by European experts into proof that American industrial methods could produce results that surpassed traditional European engineering approaches. The bridge's continuing performance through its first decade of operation validated every aspect of Washington Roebling's structural calculations and safety margins. No structural failures occurred despite traffic loads that exceeded original design specifications. The steel wire rope maintained strength characteristics exactly as laboratory testing had predicted, with no deterioration from weather exposure or mechanical stress. The web truss system eliminated wind-induced oscillations that continued to plague European suspension bridges built using traditional methods. John Roebling's twisted wire design had achieved more than spanning 1,595 feet of East River water. It had bridged the gap between European engineering tradition and American industrial innovation, proving that mathematical precision combined with superior materials could produce structural capabilities that craftsmanship alone could never achieve. The Brooklyn Bridge stood as permanent proof that American engineering could exceed European expectations through systematic technical methods rather than theoretical superiority, establishing industrial credibility that would define American infrastructure development for generations to come.